Hi, my name is Farzad Eskandanian, and I am presenting the work that I've done in collaboration with my advisor, Dr. Bamshad Mobashir at DePaul University. This work is about generating recommendations that are both accurate and diverse, and it relies on stable matching to achieve that goal. First, I'll give you a quick background about the problem and the reason why we need to consider diversity into recommendations. In past few years, we've seen a lot of works in the domain of recommender systems, but their goal is to improve accuracy of recommendations. The training data used in these works is mostly from users interacting with items in analyzed systems, for example, by rating them. But most of the times in the process of gathering this data, the items are not selected at random, meaning users are mostly rate items that are popular, and popular items are not that many compared to the total number of items, as you can see in the figure. This results in a small portion of items receiving more than 90% of the feedbacks. Measuring accuracy using the bias data favors the popular items. And since we have a long list of items that are not popular, this results in recommending only a small portion of all the items in the catalog. This is also known as the problem of fairness of exposure, where popular items have more chance of appearing in the recommendation lists. If you only recommend popular items, the measure of accuracy does not show any problems, and still we see high accuracy even though there is no diversity in recommendations. So that's why we need to consider metrics beyond accuracy for evaluation that are based on concepts like diversity or novelty. But also note that both relevance of items to the user's interest and diversity of items in the recommendation list are equally important. So we need to measure both accuracy and diversity of recommendations. The challenge is that these two objectives are incompatible with each other, and increasing diversity will result in loss in accuracy. So the main research question here is how to deal with the trade-off between accuracy and diversity. The notion of diversity that we are interested in is called aggregate diversity. If you look at the items in all of the recommendation lists for all the users, aggregate diversity is about how uniformly the items are distributed to users. So we have two objectives that we have clearly defined. First is accuracy, and the second one is aggregate diversity. Many existing algorithms have been developed to increase accuracy. So we can use the recommendations from those methods for the first objective and re-rank those recommendations in order to increase diversity. In other words, we need to develop re-ranking algorithms with the objective of maximizing diversity with minimum loss in accuracy. This is challenging because first, we mentioned that the training data is mostly concentrated on popular items. And secondly, for those niche items with few feedback data, it is very hard to separate noise from information. That's why increasing diversity is likely to reduce accuracy. To solve this problem, we've transformed this recommendation problem into a bipartite graph with users on one side and items on the other side. And edges in this graph represent recommendations. To include the two objectives that we mentioned, we consider two utilities for each part of the graph. User side utility is the same as personalization or accuracy. And for the item side, the utility of an item is defined as being exposed or recommended to a specific set of users that the item should be delivered. This notion is similar to the targeted advertising. This indicates the preference of items in terms of which users they prefer their product to be exposed to by recommendations. Note that maximizing the average utility of item side increases diversity. So then the goal is to find a bipartite graph or matching that maximizes utilities of both users and items. We define utilities based on ranking preferences. So for user side utility, each user expresses her preference in terms of a ranked list of items. And for item side, utilities are defined as ranking of users. In other words, everyone has a ranked list of the other side for themselves. Besides the ranking preferences, we need to specify some constraints because we do not want to recommend everything to everyone. There is a limitation to the number of items that is normal to recommend. And so we want to limit the exposure of each item so that we do not recommend an item more than a certain number of times. Utilities and constraints together define our main objective, which is finding a matching that maximizes user and item utilities subject to their constraints. So the matching assigns items to users' recommendation list, and the challenge is to distribute these items such that when we limit the number of times each item can be recommended, the loss in accuracy is minimal. So far, I have formalized the problem, and now I'm going to talk about the solution. Our problem is an extension of the stable matching problem. So in stable matching or stable marriage problem, we are given two sets, one for men and the other for women. And each person has ranked members of the other sex in order of preference. They want to be paired and married together such that no two people of opposite sex would rather have each other than their current partners. When there are no such pairs of people, the set of marriages is stable. Yale-Shapley algorithm is a known method that finds stable matching in polynomial time and has many real-world applications. While the stable marriage problem needs to be one-to-one matching, there is another version of this algorithm that works for the college admission problem, which is known as deferred acceptance algorithm, and requires one-to-many matching to be found, meaning each college can be matched with many students. The mechanism in all of these methods are similar, and it consists of a series of propose and rejections. In the context of our problem, a many-to-many matching is required, because each user should be matched with many items, and each item should be matched with many users. The mechanism used in the deferred acceptance algorithm is interesting mostly because it is very intuitive and easy to understand. We'll see this in the next slide. So here's how this method works. The input data consists of two ranking preferences for users and items, and two constraints for each side. We start by setting S sub U, the set of selected items for user U, to empty. Then there is the main condition for the main loop of the algorithm. We actually start counting our algorithm's steps from this point as labeled in the flowchart. So step 1 selects a user that has less than k items assigned to him in the matching mu. At first round, mu is empty, so it requires many iterations for this condition to become false. Next, we select user U that made the previous condition true and try to find the item that is preferred the most by this user and call it item I. We add this item to the set of matchings for user U and also to the set of items selected by this user. At step 3, we look at the item side preferences and make sure that item I that has just assigned to U has not been assigned more than its cap. If not, we do nothing for that item and we go back to step 1. Otherwise, at step 4, we reject the user that is least preferred by item I, and we remove that user from the matching set mu. And we go back to step 1 and repeat this process until all the users are matched with exactly k items. The longer version of this paper that is available on arXiv, we've proved and showed that the same characteristics that are true about deferred acceptance algorithm is also true about MMDA. The first one makes sure that MMDA always finds a stable matching. Second one is about the user optimality of MMDA. Since we start from user preferences and actually users actively select items in contrast to item side, that items impose their preferences in terms of rejections, the algorithm favors users more, and so MMDA finds a stable matching that is user optimal. In order to test the effectiveness of our method, we ran several experiments using 3 data sets. Moviland's 1 million, which is widely known and used in recommender systems. Also, we used 2 Amazon datasets in the domain of movies and books. The basic summary of these datasets are shown in the table. As we mentioned earlier, our approach is a re-ranking one, and so for the initial recommendations, we use 2 methods, non-negative maze factorization and user-based KNN. We generated 3,000 recommendations for each user from these methods and used them in the re-ranking methods to find the top 10 items. To compare our method with previous works that re-rank the recommendations, with the goal of increasing accuracy and diversity, we used two successful methods: Bayesian re-ranking that is proposed by Sal Vargas, and by criteria optimization using network flow that was presented at KDD 2017. We used two metrics for evaluation: precision at 10 for accuracy and gene index for aggregate diversity. In this slide, we show the results for our method for using Amazon movies dataset. In all of our experiments, since the data about item utilities were not available, we use an implicit approach, which is recommending users to items and use their scores generated from that process to indicate the ranking preferences of items. Figure 1 shows the results in terms of user and item utilities at each iteration of the MMDA. At first few iterations, you can see that the utilities are very small, and this is because there are many rejections by items that reduces the utility of both sides. But as items distribute more evenly over recommendation lists, the utilities become larger. Also, because MMDA is user optimal, at each iteration, the utility of users are greater than for items. Figure 2 shows the utility of both sides for various constraints in terms of item caps. Again, since MMDA is user optimal, when we relax the constraints, the utility of user side dominates. The main purpose of item cap is shown in figure 3, where the trade-off between accuracy and gene index is shown. The smaller gene index values indicate more diversity. So item caps let MMDA be flexible in dealing with accuracy diversity trade-off to the extreme degree of 100% or perfect diversity, which is the uniform distribution of items in the recommendation list. For cap equal to 11, we have reached the perfect diversity by losing only 3% accuracy. To the best of our knowledge, no other algorithm is capable of reaching perfect diversity with this amount of loss in accuracy. And this is the main advantage of this method. These are the results for movie lens dataset, and we compared our method to the baseline that we introduced earlier. Since we are interested in the balance between accuracy and diversity, we plotted the best result in terms of average between precision and inverse of gene index. As you can see, MMDA outperforms other methods with a large margin. In the line plot on the right, you can see that all the methods start from the orange dot, which is the base recommendation. And as they increase gene index, the precision decreases. We have highlighted the optimal or desired solution by the green region on the upper right corner of the plot. MMDA does not perform better than NetFlow for higher precision values, but for high diversity values, it has much lower precision loss. Here we show the results for Amazon Movies dataset. For this dataset, our method performs much better than the baseline, as you can see in both figures. The result for the third dataset is available in the paper. To conclude, we discussed the importance of maximizing both diversity and accuracy. Also, we formalized the problem as a two-sided system with two ranking utilities for users and items. And we argued that maximizing both utilities increases aggregate diversity with small loss in accuracy. As a solution, we generalized the known deferred acceptance algorithm for the case of many-to-many matching and adapted that method into the context of recommendation. Also, we ran several experiments to show the effectiveness of our method. Results based on these datasets show that MMDA outperforms the baseline methods. And that's it. Thank you for watching my presentation.